Hello everybody, how are you? Good evening, and welcome to our live stream, second collaboration with mathleague.org. If you were here yesterday, you saw that we tried to do some problems. Thankfully, there was a really good group of people doing the live comments because, as you may have remembered, I got one of them wrong. But thankfully, I got saved from the people who are out there. If you're new here, what you're about to see is that we're going to try to do some really interesting questions that came from the Middle School Math League competition, the most recent one, qualifying round 6. And what you'll also see is that I actually haven't done the problems before. That's on purpose. That's because the whole purpose of this live stream is to show, if you look at a question for the first time, how could you think about solving it? But along the way, I will often try to cook up a new math lesson on the spot if I see that there's some really neat pattern or something going on here. Are you ready? Let's go ahead and get started. So the first question for today is Math League's qualifying round 6 sprint number 25. A regular tetrahedron is partitioned into two objects by a plane. What is the greatest possible total number of vertices for the two objects? Whoa. Okay, so I think what this means is I need to try to draw a three-dimensional figure. That's hard. That's hard. So a three-dimensional figure looks something like this. So I'll have this tetrahedron. A tetrahedron means that it has four faces. And this is a edge in the back, okay? So this is my tetrahedron. And now I'm supposed to cut it by a plane. And so I need to have the plane cut it, and I want to have the total number of vertices for the two objects be as many as possible. Oh, okay, I see. So, for example, if I took the plane and I kind of cut through it like this, not sure if this picture makes any sense to people, but let's try to draw, how will you draw a plane that cuts through this thing? I know, I'm just going to say I have a laser that cuts through like this, okay? So you're basically looking head on. This laser is just going in and out, right? So that's like the laser cutting the plane. If I had something like that, I'm not saying that's the answer, but if I had something like that, then what I would get is I would get this whole tetrahedron cut into two parts. And the question is to find the total number of vertices for the two objects. Well, this vertex always counts, right? If I want to add up the total number of vertices, the answer is that I'll keep every one of the original vertices, and for everything else that I cut that makes a corner, I'm actually going to get two new vertices, right? One for this piece and one for that piece. So what this is telling me is I want to figure out how can I try to cut this so that I'm going to get as many vertices in the crossing as possible, as many vertices, and when I cut it, I want to have as many of these corners as possible because each one of them gives me 2. And the answer is going to be 1, 2, 3, 4, plus 2 times the number of new corners. Okay? So the answer is going to be 4 plus 2 times the number of new vertices. Okay, well, if I want to do that, now I need to say, how do I get a vertex anyway? Well, a vertex is a corner, and a corner comes from 3 planes intersecting. If I just have 2 planes intersecting, that's just going to give me an entire edge, right? So if you see what's going on here, it's like wherever I had an edge of the old one, where that hits this new plane that I'm cutting, that makes a vertex. So my real question is, how many of these edges can I hit at the same time? I see that I can hit 4 of them. And now I'm trying to see, can I possibly hit 5 at the same time? Oh, here's why you can't. The reason you can't hit 5 at the same time is because if I wanted to hit 5 at the same time, well, I would only get to miss one of them, right? If I want to hit 5 at the same time, I can only leave out 1. But you know what? If you just leave out this one, the tetrahedron's symmetric. It doesn't matter which one you leave out. They're all the same. If I leave out this one, then somehow I need to hit this one, and this one. Is there any way to slice this so that I slice through all 3 of the sides of the triangle at the same time, where I'm not going to run through the corner because that's just wasting. I wouldn't get any new vertices that way. Well, if I look at it that way, then it's like, oh, there's no way I could hit all 3 of these edges because it's like I've got a triangle. How could you possibly cut the triangle in a way that your line hits all 3 of the edges? You can't. So I'm seeing that right here. I'm going to get 4 plus, I'm going to get 1, 2, 3, 4 more. So I think the answer is going to be 4 plus 2 times 4, which is 4 times 3, which is 12. Okay, a little bit of me is just checking, you know, what if I tried to make this one also hit one of those vertices? Well, if I did that, then I effectively only split that vertex into 2, right? It's like there was one vertex before, and now I'll kind of split it. I count it twice. It'll be on both of the parts. So I'll just get +1. That's not exciting at all. So it looks like I want to get 2 times the new vertices. I'm going to propose 12 for the answer. And let's see if the answer is actually 12. It is. We're correct. But you can see how we thought through this, right? We were trying to make sure it wasn't just like, hey, let's try to draw it and see what happens. Okay, next question. Number 26. Maya places a token on one of the squares in a 3x3 square grid. The token can move one space up, right, down, or left, but it cannot revisit any square that it has already visited. If Maya can choose where to place the token, how many possible paths for the token cover every square in the grid? Oh boy. Okay, so I'm trying to walk through a tic-tac-toe. That's what's really going on. Let's draw it that way. So I have a tic-tac-toe, and I want to first know, like, what kinds of different ways can I walk? So I want to be systematic about this. I could have that one of the endpoints is a corner. If one of the endpoints is a corner, let's just start doing something and see what happens. I clearly need to make a bigger tic-tac-toe board. Bigger tic-tac-toe board. If you start in the corner, you know, here's one kind of thing you could do. And I'm seeing already there's a lot of different things I can do. So I'm going like, if I start in a corner, let's just write all of the ones which start in corners first. Oops. Okay, and if I start in the corner, I guess I could try going all the way over. Wow, there's lots of these. Because what I'm seeing is that we might have some work to do to try to make this thing systematic. Okay, so I already saw the ones where you're starting in corners. I'm also curious, can you start not in a corner? Okay, well, let's try to draw a few of these first and see. Wow, this is hard. Okay, what else do we have? So if you start in the corner, you know, I'm trying, the way I'm systematically doing it is, I was like, what if I go all the way across? But, yeah, so the way I was thinking is like, well, from the corner, you're going to go one way. Either you go across or you go down. So I'm just going to say, here are all the ones where I go across, and there'll be like double it in some sense. We'll have to deal with the symmetries, okay? So, good. And I see people are saying like you can't start at the top edge. I see that too, but I have to double check that. But I'm like, let's try to draw all the different looking things, right? So if I started going across, well, I could keep going across, or I could try to go across and then I could go down. Is there anything interesting that happens there? Oh my gosh, there is. You can do interesting things there too. Oh, interesting. But that one looks like that one. Oh, so now I'm curious, are there any substantively different ones, right? These two are the same. Up to some kind of symmetry where I rotate or I flip, okay? But I'm also curious, is there anything else I could do? If I went across and I went down, well, I can't cut myself off and I can't go that way. So that's interesting. So if I go across and then down, I actually am forced to come back and then I'm forced to finish this way. There's no choice. So that tells me this is not any different from that one. Okay, well, I dealt with the case of going across and then down. Let's go across and then across again. But then if I go across and across again, that's like I have to go down. And now I either go left, this was go left. If you go left, yes, you have to go and finish it this way. And if you go down and you go down again, you have to finish it that way. So what I'm seeing is that if I go from the corner to the corner, I just have these two possibilities. What if I don't go from corner to corner? What if instead I try to go from this thing? I see some people saying it's not possible. We'll find out soon. So if I start from here, I have only two possibilities. I could go like towards a corner. Oh no, it's dead. Or I could try to go towards a corner and try to go around somehow, but no, it's not going to work. It's just not going to work. Okay. Or else I could try to go down, but then I'm also not going to work. Yeah, you can't start from this side. You can't start from the middle of the side. And what if I started from the center? Well, if you start from the center, you're going to end somewhere. And we already know that the end won't be one of the edges because you can't have something which starts from one of the edges and start and end. You can just go backwards. And if you started from the center and ended at the corner, well, you'd have caught it in that case. So what I'm seeing is that there are these two possibilities. It's going to be one of these two. Okay, well then, now I just need to know how many different ways I can make these kinds of pictures. So if I look at this picture, staring at it, I'm just saying somehow with this picture, I see that it's either going to be this way. You start, it's going to be from corner to diagonally opposite other corner. That's how it is. And it either goes like horizontal or it goes vertical. I mean, there's another version of this which is going vertical. Oops. Vertical like this, right? We've got vertical. So we've got horizontal, we've got vertical, but we also have the backwards. We can also flip it this way. So you could start from this corner and go across the other way. And you can also flip this one. So what I'm seeing here is that I'm seeing 4 of this type. And the easiest way to think of it is that if I want to know what this type looks like, I'll be going between 2 corners. So it's either going to be these 2 or the other 2. And once I decided which 2 corners, it either goes across or it's either like more horizontal or more vertical. So there's 4 of those, I think. This is a hard problem, easy to make mistakes. So we'll find out at the end whether it's right or wrong. So I'm like, I think there's 4 of this kind, okay? Oh no! Okay, I already saw people say in the chat, mistake, I forgot the spiral. You're right. So I would have gotten this question wrong, by the way. So I would have gotten this wrong, but thank you very much. People here have just pointed out that we forgot the spiral. And that was because, I did it too fast as I was checking the possibilities. Thank you, everyone. I'll use a different color just to emphasize that's the one that I forgot. Because I was like, if I go here and then go here, there's nothing else you can do. I already got all the cases. No. There's that one. So I would have gotten this wrong. There was that one that we missed. And I'm putting this in a different color because we'd have missed it. And the spiral from the corner to the center is the same as from the center to the corner. So we'd have both of these. Okay? So that we have dealt with the case of if one of the endpoints is the center. All right. So now we got this one. Now let's go and see this kind. How many of this kind are there? Well, it looks like the way you can think of this kind is you're going from one corner to another corner that is on the same edge as it. And I could even think of it as like starting on that one and ending on that one. In this case, it's not symmetric. This one was symmetric. If I started from here and ended on there, and started from the other one, ended on there, this is the same picture. Well, in the sense that it's either like more horizontal or more vertical, right? So the way I think of this is, well, I can think of which corner wants to be the starting point of this. There's 4 choices, right? There are 4 choices for the starting point there. So here, for this one, there are 4 choices for which is the first corner where I start this. And wherever I decided to start this, I could either end at the one on this side or the one on the other side. There's like 2 other corners I could end at. It's either the one, I guess, horizontal or vertical from where you are. So I'm getting 4 times 2. And that's, again, because I can think of it as that's the starting point and that's the ending point. All right? So that would be 8. And now there's this kind. How many of this kind are there? Well, if I'm going to do some kind of a spiral, oh, this is nifty. Because if I do the spiral this way, I can get there. But there's also this other spiral where I start from the same corner and you go the other way, right? So what I'm seeing is that from every corner, I have 2 ways I could go. I could spiral like, what is this? This is clockwise, or I can spiral counterclockwise. So on this one, what I'm seeing is that there are 4 ways to choose. Let me use the bad color because I got it wrong. 4 ways to choose which corner you start at, times 2 directions that you could spiral, right? So in that case, I will have to make sure that I have to add this too. So I have 4 times 2, 4 times 2, and 4 times 1. Altogether, that's 4 times 5, because it's like 1 4, another 2 4s, and another 2 4s, and I can count on my hands. 4 times 5, I'm coming up with the answer of 20, which I'm going to put in this pinkish color because I actually got it wrong. I would have put out an answer of 12, not 20. Oh, somebody says the answer is 24. We're going to find out soon. And the answer is 40. Oh no! Okay, that's not good. We're missing a whole lot of them. So what just happened here? Oh, yeah. Of course. I can go on each one both ways. I can go on each one both ways because I read it wrong. Not that I read it wrong. I thought about it wrong. I didn't read it wrong. I read it right. It's just like, look, if I draw one of these pictures, so what we were counting is how many pictures there are. And we forgot that you can go around each picture both ways, right? So the deal is, yes, we just counted pictures, but remember that these are supposed to be paths. So we want to know how many possible paths are there, where the important thing about paths is the path isn't just the trail of the path. The path is like, are you going that way or are you going the other way? Right? They never said you can't do both ways. So yes, indeed. So yeah, again, the way I did this is I counted like how many trails there might be. But actually the question, is asking how many ways you could move it. So you have to remember that you could go on each one each way. So it is 40. So it's we can't use that color either. So it's 40. Okay. All right. Well, in that case, thank you to the group here for helping me at least get to 20. But we had a double mistake. And as I've said in other live streams, this just proves that 2 wrongs don't make a right. Okay, let's keep going. Next question, number 27. Can we do this one? The prime factorization of 1003 to the power 4 and then plus 1 is 2 times 97 times p. What is the product of the first and the last digits of p? Whoa! Okay, so it looks like I just need to divide 1003 to the power 4 plus 1. I need to divide that by 2 times 97. Because supposedly the last thing is just going to be the prime p. Okay, let's see if there's some way to do this. Because it's like 2 times 97 times p, so I just need to divide. So I need to know what is 1003 to the power 4 plus 1, and then divide by 2 times 97. What's that? Well, that's like 2 times 100, which is 200, but minus 3 and then minus 3 again. Because this is 3 less than 100, so I need to minus 6 from 200. That's 194. Okay. The reason I did this is because I can get you the first digit if I do a division, right? If I want to do 1003 to the power 4 plus 1, what is that? What's 1003 to the power 4? Well, I'm just curious what the beginning of it is, right? Because then I'll just divide by this 194. And I'm now going to use a way of thinking about how you take something to the 4th power. I didn't realize that your questions are this hard. And they're very interesting too. But if I have 1000 plus 3 to the power 4, there's a way to raise this to the 4th power using something called the Binomial Theorem. The Binomial Theorem says that if I want to do this, it's going to be 1000 to the power 4 plus 3 to the power 4. But I left a lot of space in between because it's not just going to be this plus this. I don't actually have the time to teach you the whole binomial theorem here, but I will say it's something that comes from combinatorics and algebra. Oh yeah, that thing. That's right, Daniel Guo, that thing. That thing is that if I want to do... Oh, you know what? I'm just going to teach it to you. I just can't bear to not teach it to you. I can't bear to just use it, okay? So here's what's going on. 1000 plus 3. If I've got 4 of them, 1000 plus 3. Yeah, just something makes me feel bad about just using something with no explanation. So here we go. Let's explain how this works. Suppose I want to expand this whole thing out, okay? The way you expand this whole thing out is you want to know how many ways are there to... Not how many ways. You want to collect all the different ways where you grab something from here, something from there, something from there, and something from there. You're going to get 16 stuff altogether, where you have to choose something from each. Where does the 1000 to the 4 come from? It's when you pick the 1000 from each one. Right? There's like one way. Just pick 1000, 1000, 1000, 1000. But there's also a way that you can pick 3 of the 1000s and 1 of the 3s. So there should be another term, which is something like 1000 cubed times 3. Right? Except that I left some space here because, you know, if you're going to pick 3 of the 1000s and 1 of the 3s, there's 4 ways to decide, you know, which of these brackets you pick the 3 from. Like 1000, 1000, 1000, and then the 3, that's one of these. But you could also do like 3 and then 1000, 1000, 1000. So in fact, what you need to multiply this by is the number of ways that you could choose 1, 3 from 4 brackets. That's 4 choose 1, which is 4, which you can see here. Okay? And the next term, I'm missing some, I don't have enough space here, so I'll write some more terms. The next term is going to be 1000 squared times 3 squared. But if you see how to make that, if I want to do that, I need to know how many ways can I pick 2 of the brackets to grab 3s from. That's 4 choose 2. So that's 6. Okay? And the 3 to the 4, let's leave some more space. The next one is going to be 4 times 1000 times 3 cubed, and the last one will be 3 to the 4th. Okay? So that's going to be this number. If I wanted to know what is 1003 to the 4th power, I'll have to add 1 at the end. But the reason I'm doing this is I'm curious. Oh yeah, I've just proven this to you now. This is called the Binomial Theorem. Also known as, oh, that thing. Okay, so this is what we used. Now, the reason I did this is because I'm pretty excited about the beginning of it. Because, you know, when you do a division, if I want to know the first digit, I just need to know what this starts like. Can anyone tell me what this might look like? If you try to add all this stuff together, what does the beginning look like? 1000 to the 4th power plus 12 times 1000 cubed plus some other thing plus some other thing. Well, actually, the beginning of it, well, I need to do some place values, right? So if I want to know what this thing looks like, it's going to be the 1000 to the 4th power is 1. Oh, that's why commas were invented. Let's use commas. How convenient. That's your 1000 to the 4th power, right? Yes, I can count. That's 1000 to the 4th power. Oh, yes. And somebody said Pascal's triangle. 1, 4, 6, 4, 1. Yes. Binomial theorem, Pascal's triangle, chooses. They're all related. Okay, so now I've got this thing. The next thing I want to do, that's the 1000 to the 4th. What's this guy? This is 12 and then 1000 cubed. I want to add these all together, right? And what's the next term? Oh, even smaller. What is this? Could I actually do that? 6 times 3 squared. That's 6 times 9. That's 54. And that will be 54 million. And so on. There's a reason I say and so on. Because if all I care about is to divide, right? If I want to divide this whole blah, blah, blah by 194, I don't care about the rest. You know how you do the division? It'll go 1012 blah, 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 blah divided by 194. I can do that. Except I forgot the number. Okay, 1012, right? So 1012, just kidding, I need more space. 1012 blah, 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 divided by 194. See how this works? If I just care about the first digit, I can see it. It won't work here, okay? That'll be like 0. So I need to know how many 194s are in 1012. Remember, 194 is really close to 200, so I would try 5. And that's probably right, because somehow, if I want to multiply 5 by this 200 minus 6, then the answer will be 5 times 200 minus 5 times 6. And 5 times 200 is 1,000. 5 times 6 is 30. So that's like 970. I think. I hope. I can see that. Yes, because 5 times, I'm double checking this. 5 times 19 is 95. And 5 times 4 is 20. So this works. So now I know that the first digit is 5. Now the only thing I need to know is what's the last digit. Well, if I add all this together, the last thing I'm going to get, oh yeah, I do need to know this, plus blah, 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 plus all the way down to 81. Okay, so now I know it ends in 82, right? So now I happen to know, I need to know the last digit of this prime p after I divide, and I'm curious if there's any shortcut that I could see. So, this is not fun, because I'm trying to say I don't actually want to do this division. That would be no good. So I see that it's going to end in a 2, and I'm thinking of what my possibilities are. Oh, I have some options, okay? So I'm going to see that the top of the number is like blah, 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 2, right? It's going to, actually it's blah, 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 8, 2. That's what I know, because I have to add the 1. So it's blah, 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 8, 2. Do I know anything about blah, 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 8, 2 divided by 194? Somebody's telling me it's a prime. So now the thing I'm curious about is, well, 4 times what would give me a 2? Because the thing about prime is like, well, it better be an integer, right? That's really convenient. It's an integer. So now I want to know, if I took 4 times what makes 2? Well, 4 times 3 makes 12. 4 times 8 makes 32, right? So I'm thinking about like what that last digit could be. The last, because if I'm going to multiply 194 by something, some horrible number, well, that horrible number, if it ended in a 5, then I would get 4 times 5 is 20, and there would be a 0 there, and it would be bogus, right? And I think that the only things I can do to end in a 2 are 4 times 3. Oh, let me write it more carefully. blah, 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 blah 3 times 4 equals blah, 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 blah 2. Blah, 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 blah 8 times 4 equals blah, 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 blah 2. Right? And actually, there's a nice thing. From 3 to 8, it goes by plus 5. That makes sense because blah, 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 blah 5 times 4 ends in a 0. And that's actually why these have the same last digit. So now my question is, can you think of any primes, which are integers, by the way, which end in 8? No. So it's got to be 3. Do you see how this works? There's no primes that end in 8. So this is no way. Bad. This is a bad prime. Primes, there's like, come on, there's no even primes. No, that's not true. But there's like no like very even primes. Actually, that's also kind of bogus because just because it ends in 8, it might be like 18 and it's not really very even. So I think I'm just going to write no even primes except just plain 2. Okay? So in that case, what I know is that this is bad. Therefore, it ends in 3. So I think I'm done. That means that it ends in a 3 and it starts in a 5, right? So read the question again. The product of the first and last digits, well, it starts in a 5 and it ends in a 3. So 5 times 3 is 15. Let's try 15. And let's see if that's the answer. It is! And we got it. Okay, that was fun. That's a really neat problem. And if you can see, like, we didn't actually have to divide everything. Although if you really wanted to, you could have divided out the entire thing and gotten the answer also. But you all know me. I'm too lazy for that. So there has to be some other way to do this problem. Let's do another question. Whoa, time to read a question. Question 28. Murray is busting ghosts using a trap that costs him $1,000. Every day, Murray has to use his trap in a building with 4 ghosts, and the trap catches each ghost with probability 1/2. He will be paid $0 for failing to catch any ghosts, $1 for catching 1 ghost, $3 for 2 ghosts, $6 for 3 ghosts, and $10 for 4 ghosts. The trap is good for up to 1,000 days. What is Murray's expected daily profit from busting ghosts in dollars over the course of these 1,000 days? Express your answer as a decimal to the nearest hundredth. Yes, I think that is a lot of ghosts. I'm trying to understand, first of all, can you bust the same ghost more than once? How does this work? So you're using a trap, and you gotta use the trap, and the trap catches ghosts, and you get $0 for no ghosts. And it's good for up to 1,000 days. It does seem to me like the ghosts don't respawn. I think that's how this works. Okay, I think I understand. Because it says the trap is good for up to 1,000 days. If it was like you're going to play the same game every day and the ghosts show up again and start haunting you, then it wouldn't say you can use the trap for up to 1,000 days. It would just say use it for 1,000 days. There's also this thing about a decimal to the nearest hundredth. And what this means is it's probably going to converge. It'll probably be something which the answer gets smaller and smaller. I mean, sorry, it gets closer and closer to some answer. Okay. And by the way, he's probably going to catch some ghosts, right? If you got this thing and you got probability 1/2 for catching each ghost, eventually you'll probably catch them. Wait a second. Now I'm really confused. Because it's like, won't he probably catch all 4 ghosts eventually? First of all, wait. Now it's also more complicated for me because it's like the trap costs him $1,000. So I'm trying to understand the question here. So trap costs $1,000, and it's supposed to be an expected daily profit over the course of these 1,000 days. Because it's like, if you could only catch up to 4 ghosts at all, then you can only make up to $10 at all, and then you paid $1,000 to start. So that's not very much profit, not very good. I think what's actually going on is they're respawning. So I'm going to make a guess. I'm going to interpret this question to mean that every single day, 4 ghosts appear. Okay, we're going to interpret it that. Yeah, so the ghosts are probably respawning. So it's like every single day, it's like, poof, 4 ghosts show up. And then now we just need to know what is going on with these 4 ghosts. Okay, well now we just do something where we find the expected number of ghosts, expected value of ghost catching for the day. Let's do that. Okay, So in that case, let's write down the payoff, okay? Payoff's in green because at least in America, the cash is green. So the payoff, oh, I need to say the number of ghosts. That should be white. Okay, so ghosts. The number of ghosts caught. Either 0 or 1 or 2 or 3 or 4. You got the payoff. It's in dollars. I'll just write the units are dollars. And the payoff was what? It was 0, 1, 3, 6, and 10. How cute. Those are like triangular numbers. Okay, and if I want to find out my expected payoff, I need to know the probability of each one. Expected just means average. So for example, if you were like a super awesome ghost buster, then suppose you always caught 4 ghosts, then it's like obviously your expected value is 10. Or on the other hand, if you were like an all or nothing ghost buster with half the time you actually catch all 4 and half the time you catch none of them, then your expected value you'd expect to be like halfway between 0 and 10. And if you have instead this like very interesting ghost busting capability where, you know, it's a half chance of catching every ghost, then we need to write down the probability that you land at 0, 1, 2, 3, or 4 ghosts. And we've actually seen these numbers before. So this is what we just saw. The probability, well, what's the chance that I get no ghosts? It's just half times half times half times half, because for each of the 4 ghosts, you had a half chance of getting it. That's 1 over 16. Now, what's the chance of catching them all? Well, for each of them, it's a 1/2, and a 1/2, and a 1/2, and a 1/2, right? Because I got these 4 ghosts. Hey, it's Pac-Man! That's what this is! This guy's just playing Pac-Man. I just figured it out. He's just playing Pac-Man. Anyway, so we got these 4 ghosts, and in Pac-Man, they respawn. All right. Actually, I don't know if anyone here even plays Pac-Man anymore. Pac-Man was this super cool game in the 70s or something. Anyway, so let's keep going. Now I need to know the things in the middle. And here's where the chooses come. Because, you see, if I've got 4 ghosts, and I want to know what's the chance that I catch just one of them, it's just like that thing we just saw with the 1000 plus 3 to the power 4, right? It's that 1, 4, 6, 4, 1 is going to show up again. It's, again, 4 over 16, because first I decide which of the 4 ghosts I catch. And then now that I've decided it's going to be the purple ghost, right? Is there a purple ghost in Pac-Man? Anyway, it's going to be the purple ghost. And so we're going to do this 1/2 chance that you don't catch the green ghost times 1/2 chance that you don't catch the yellow ghost times 1/2 chance that you do catch the purple ghost times 1/2 chance that you don't catch the pink ghost. Half, 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 half. They're all half. So it's going to be 1/16. And there's 4 ways to decide which of those 4 ghosts you caught. Similarly, for the 3, it's which of those 4 ghosts didn't you catch? Or it's 4 choose 3. How many ways can I choose 3 ghosts to catch? So it's 4 over 16 here. And this one's 6 over 16. That was the 4 choose 2. All right, so now the game becomes, how do I find the expected value? Well, you actually multiply the probability by each payoff. You can think of it as being like, well, there's a 1/16th chance that I get 0, plus a 4/16th chance that I get 1. So 4/16th times 1 is like how much of the 1 I get. Does that sort of make sense? It's like I have $1, and what's the chance you're going to get the $1? 4 over 16. So how much of the $1 are you getting? Just 4 over 16 of it. So we're going to just multiply each of these vertically and add everything. So the expected payoff per day, remember this is a per day thing, I have to multiply each thing and add. So I like multiplying by 0. I like 4 over 16 is 1/4. This, let's quickly say, what's this times? No times, plus. Simplify, 6 over 16 is 3 over 8. Yeah, 3 over 8 times 3 is 9 over 8. Plus, that's another 1/4. 1/4 times 6, that's 3 over 2. Plus 10 over 16, that's 5 over 8. Okay, addition time. So 9 over 8 plus 5 over 8, I'll do first, because that's going to get rid of my 8. Because 9 plus 5 is 14, which is going to divide by 8 will be 7 over 4, right? And that 7 over 4, let's draw arrows. I didn't do the 3 over 2 yet. Next I'm going to do the 7 over 4 and the 1 over 4. That's just plain 2, because that's 8 over 4. That's 2. And so I have 2 and 3 over 2, which is going to be, that's 1.5. So I have 3.5. Man, this guy is making a big bucks here. He's doing ghost busting, and every single day for all his work busting those ghosts with the traps, he's going to have an expected earnings pay of $3.50 per day. But don't forget that he has to pay for the trap. So the trap, he's busting some ghosts, and the trap costs him $1,000. Well, it's good for up to 1,000 days. That means that every day he's going to pay $1 for the trap, right? Does that make sense? So you lose $1 for the trap. And so I need to say that the answer is the 3.5 minus the trap, and it's just $2, 2.5. So I'm going to get 3.50 minus the dollar is equal to 2.50. And let's try that as the answer, okay? Let's see if this works. All right, I don't know if this is correct because maybe I misunderstood the question, but let's try. It's correct. So now you know. He gets $2.50 a day for busting ghosts. Busting ghosts sounds like dangerous business. I will say this is a pretty hazardous job for $2.50 a day. But then again, maybe he just likes busting ghosts. And if that's the case, then $2.50 is like, he's free money. Actually, I have a colleague, another professor at Carnegie Mellon, who says he can't believe that he's being paid to be a professor because he's just doing what he wants to do. So maybe that's what this guy loves. This guy just loves busting ghosts, $2.50 a day. It works. All right, let's keep going. Oh, but how many ghosts are in your area? Yeah, you're right. So I think this also means that the other thing you could do is maybe you could try to go to an area that has more ghosts. Let's keep going. Question number 29. What's this? Oh, okay. So somebody was looking at somebody gave me a comment on somebody gave me a comment on YouTube, which was a different topic. But let's do this. Question 29. Two real numbers, a and b, are independently and randomly selected between 0 and 10 inclusive. The numbers satisfy the inequality a plus b is less than or equal to 10. What is the probability that 2a plus 3b is less than or equal to 10? Express your answer as a common fraction. Are these actually middle school questions? This is hard. I mean, I'm impressed. I think what this means is that just since middle school students these days don't spend all day playing Pac-Man, they're much smarter than we used to be. So what I see here is they satisfy some inequality, okay? Independently and randomly selected. This is a conditional probability problem, okay? So whenever I have something like real numbers, I draw some kind of a graph, okay? So let's draw a chart. Oops. My pen came apart. Let's draw a chart. These are the axes. 0 is there, 10 is here. 10. Okay? Now, if I'm going to pick two numbers independently and randomly selected between 0 and 10, it's sort of like I've got all of this square. Let's draw a square. Let's pretend that went down at the 10. Oh, there's an easier way to pretend. You just erase that tick mark. Now it did. Okay, so you picked something in here. It was like kind of smoothly distributed. You can pick anything inside there. And the way you think of it is, it's like everything in there has equal chance. We're going to think of this as what's called geometric probability. So the next thing we do is, but look at that. The numbers satisfy a plus b less than or equal to 10. What's a and what's b? Let's call that a, let's call that b. If a plus b is less than or equal to 10, what that's telling you is, but just kidding, you didn't pick that one. You didn't pick this point I'm pointing at, because over here, that's like 9. 9 plus 9 is 18. It's not less than or equal to 10. So let's go and bust out half of this. Well, okay, I already told you what it is. Let's bust out the bad parts of this that it can't be in, because the second piece of information told me a plus b less than or equal to 10. Actually, what does that region look like? What part of this square is also in the region where a plus b is less than or equal to 10? If you haven't done this that many times before, I'll just do it slowly. If I think of it as like y equals mx plus b type thing, if the b is the y-axis, I can write this as b less than or equal to 10 minus a. That's like slope-intercept form for slope of -1 and intercept of 10. But if you have done enough of these questions, you sort of know that it will look like that. So the inequality a plus b less than or equal to 10 is this b less than or equal to 10 minus a. So it's like down here, okay? So I know that I'm going to pick up something in this part. So now I know that what I've picked is something like smoothly random from this place. Now the next thing I need to ask is, what's the probability that 2a plus 3b is less than or equal to 10? Oh, let's go and draw something which just says what part of this region also satisfies that. It's time to do the slope-intercept again. So if I do this again, 3b, oh, I'm so scared of b's. B's look like 6's. 3b less than or equal to 10 minus 2a. So b less than or equal to 10 divided by 3 minus 2/3 a. Okay. So now I have to draw this kind of the thing that goes like from 10 over 3, which is 1/3 of this, going all the way down. Oh, let me tell you something neat. You can use this to find the two intercepts. The intercepts, so this is going to be aligned with a negative slope, right? It's going to start from here and it's going to go down. And I'll tell you what it is first, and then we'll see how we could have gotten that easier. This is 10 over 3, which is 1/3 of the way up. And this is going to be 10 over 2, which is also known as 5. I'll write it like this. This is 10 over 2, aka 5. AKA stands for also known as. And this is what I've got. And let's highlight this part in yellow. Okay, so now, how did I know this? Well, there's two ways. One is I could have said, we start from the 10 over 3. Then you go down with a slope of negative 2/3, which means that you go down 2 for every 3 you go across. And so you could do some calculation and be like, yeah, so I take this guy divided by a 2 and then times a 3, it's here. That's one way. But the other way you could do this is you could say, where are these intercepts anyway? When in this thing, if I have equality, when is a equals to 0? A equals 0 means it's on this line. Well, if a equals 0, boom, that's gone. So it's just 3b equals 10. That's 10 over 3. That's nice. And then now over here, what's the deal over here? Well, this is when b equals 0. If b equals 0, boom, that's gone. And when is 2a equals 10? Divide by the 2, that's 10 over 2, aka 5. So that's like the fastest way to do this kind of a thing. That's also another way you could see the intercepts of this. The intercepts of this are when a equals 0, b is 10. When b equals 0, a is 10, and it's a straight line. But now all I have to do is I have to say, what's the probability that if I have a random piece smoothly from this purple stuff, that it happens to be in the yellow? That's a ratio of areas. I just have to go and take the area of the yellow thing divided by the area of the purple thing, right? So now it's area time. Oh, I'm too lazy to calculate the areas. I'm going to do it another way. I'm going to say that this is 1/3 of that. And this is 1/2 of that. If I thought about half base times height, what I'm saying is my base is half of the other base, and my height is 1/3 of the other height. So my area is 1/3 times 1/2 of the original thing. Does that make sense? That's actually quite nice. So now I know that the yellow area is equal to 1/3 times 1/2 times the pink area. So the answer is 1 over 6. Okay, and somebody said similar triangles. It's not exactly similar triangles. A similar triangle, you'd actually have to have that the angles matched, and the angles don't match. On the other hand, if you happen to have, in any case, if you happen to have like a triangle like this, it doesn't even have to be this thing which was 90-degree angle. In fact, it's still true that if I just take like some fraction along this side and a fraction along that side on any old triangle, then the area ratio is also the same. And you can prove that with thinking about the ratios of the bases and heights as well. Or you can use trigonometry. Either one works. So I think this is okay. Just reading the question again seems reasonable. Let's try. 1/6. And it's good. Okay, how are we doing on time? Let's see if we can do one more problem. I often like to leave like some random Q&A at the end. So let's do one more problem and then see what happens. Ooh, the hardest problem, number 30. We might not have any time at the end. Let's try. Let triangle ABC have AB equals 5, BC equals 6, and CA equals 7. It's time to start drawing this down. So I have AB, BC, and CA, and they're all like different lengths. So I need to draw my standard scalene-ish triangle. How do you draw a scalene-ish triangle? Maybe like this? Sorry, it's just sticking out, but that's... Oh, I know, I can fix that. I can just draw it again. Okay, so this looks like 5. Maybe this guy is 6, and maybe this guy is 7. So that was AB is 5 and BC is 6. So A, B, and C. Okay, and it's sort of to scale, not really. But the way you can think of it is if you want to know which is the longest side is always opposite the biggest angle. That's actually also true. So anyway, wait a second. That's wrong. The biggest angle. Oh yeah, that's the biggest angle. This is bigger than that angle. Oh no, then it's wrong. The biggest angle, that should be the 7. That should be the 7. The way you do this is in a triangle, the bigger the angle, the bigger the opposite side length. And this looks bigger, therefore I'm going to label it the other way. Let's call that 7 and let's call that 6. And let's flip these around. So I have A, B, and C. Okay? Now, angle B is the biggest from the hinge theorem. I'm not sure if this is called the hinge theorem or not. I just call it, that thing. Actually, it's related to something called the law of sines also. That's from trigonometry. But we don't need to go too deep into that here. Next, I have points D and E lie on AB and BC. Okay, so I'm going to have a D and I'm going to have an E such that AD times DE. Oh, but the DE is parallel to AC. Let's draw that. So I have a D and an E somehow doing something. Parallel. And I have a D and I have an E. Okay, so now I have this AD times DE is supposed to be 63 over 20. And okay, I've got some parallel. If the largest possible area of trapezoid ADEC can be expressed as, so I want to make this thing as big as possible, as something, okay, I'm supposed to go and figure out A, B, and C. This is just like reporting your answer when you have some square roots. So the real game is, I want to have that this times this is 63 over 20 while also being parallel. And I'm also supposed to get this trapezoid as big as possible. Well, if I want it to be as big as possible, since that 7 is fixed, I just want this DE to be squished as far out this way as possible. Okay, so I guess now I've actually got to go and parametrize this. I need to go and think about if I have a particular variable, let's choose a variable that's convenient and then decide what I could do to go and find out all of these different lengths. And I'm going to tell you, I think that the variable that's going to be convenient, let me clear out this 5, I'm going to call this part x. And then this part is 5 minus x. Now you might say, why didn't I call that part x? The reason I didn't call that part x is because the x is giving me a ratio, x out of 5. It's more convenient because you see, how long is this DE? DE happens to be x out of 5 times 7. I now have similar triangles. The triangle BDE is similar to the triangle BAC. Therefore, if I'm going x out of the total of 5, then my long piece is x out of 5 times 7. Okay? When does this class end? In about 12 minutes at 9 o'clock p.m. Eastern Time in the US. So that means I now know that this thing is going to be x over 5 times 7. Let's call it 5 over 7 times x. Wait, what did I just say? No. It's x over 5 times 7. That's 7 over 5 times x. Okay, good. So now I just need to get the largest, now I need to get that 5 minus x times this 7 over 5x. That's supposed to be this mysterious number, 63 over 20. Let's solve for x, right? That's all I've got to do. And it says the largest possible, so maybe I've got two choices for x, because maybe I've got a quadratic equation. So 5 minus x times 7 over 5x, okay? That's supposed to be equal to 63 over 20. I hate fractions, so let's go and clear the fractions. Multiply both sides by 20, and what I'll get is 5 minus x. That gives me 28x is equal to 63. Now I guess I just have to go expand this out. So I will get 5 times 28. Well, the easier way to do that is 10 times 14. Divide the 28 by 2. I mean, throw a 2 from the 28 into the 5, get a 10. So you get 140x minus 28x squared is equal to 63. Let's go and rearrange everything so I have a nice positive x squared. That makes me happier. So I have a quadratic equation, 0 equals 28x squared minus 140x plus 63. Now, I'm seeing a lot of 7s everywhere, because 28 is a multiple of 7, 140 is a multiple of 7, 63 is a multiple of 7. Divide things out. I don't like big numbers. So if I divide by 7, I get 4x squared minus 20x plus 9. Now, can anyone factor this? Yes, I can. So I'm not sure if this is how you guys think of it in your head, but if I have like a 4x squared, I have a minus 20x, and I have a plus 9, oftentimes when I'm factoring, I sort of think, how do I do something to get a 20? I could do it with like a 2 and a 2. Of course, they have x's. I mean, the x is not the important part, but it's a 2 and a 2. And with a 9, I'm like, could I possibly make a 20? Well, if I've got 2s, I could try to make a 10, and I can with like 9 and 1. Just with negative signs to go and get the negative 20. Because then the way you do this is you kind of multiply this way and this way. And if I did that, I would get 2 times negative 9, 2 times negative 1 is 2 times negative 10. Boom, you got it. Okay? Somebody said use Po-Shen Loh method. Yes, there are many ways to solve quadratic equations. In this particular case, because it happens to be a math contest problem, my instinct was probably it can be factored. And because the numbers are small enough, I was like, I can probably see this. All right? So now let's keep going. That means that 0 equals 2x minus 1, 2x minus 9. So I have two choices. X equals 1/2 or x equals 9 over 2. Those are the two ways to make these 0, right? If this guy is 0, 2x minus 1 equals 0, then 2x equals 1, divide by 2. Or 2x minus 9 equals 0, so 2x equals 9, divide by 2, x equals 9 over 2. Which of these is better? Well, if you look at the thing we had, I always want to check for bad solutions. Could it be that is x out of range? X is supposed to be between 0 and 5. And what I see here is, no, it's not out of range. Both of these are between 0 and 5. So which one do I want? Well, I want the biggest possible area. So I better choose the x equals 1/2, this teeny weeny bit. So I'll have x equals 1/2, and now I just need to know what is the area of that trapezoid. Ah, neat. Okay. I'm going to go to one more screen. I think the answer is not on the next screen. So the next thing I've got is I've got this triangle, 5, 6, and 7. Okay, 5, 6, and 7, sort of a triangle. I have this thing here where I cut it, really close. Looks sort of parallel. And I now want to know what's the area of the trapezoid. Let's use fractions again. Because if this happens to be 1/2, then with what we just did, the fraction of the whole area that I have, this is 1/10 of the side. So this is also 1/10 of the side. So this tiny little thing is 1/10 squared of the whole thing. Similar triangles again. And so importantly, that length is 1/2 out of 5. So this is 1/10 of the entire piece. And therefore, this is also 1/10 of the entire piece by the similar triangles. So what I now know is that this area is equal to 1 over 100th of the whole triangle. And I'm going to check, what is the question asking? Is it the area of the trapezoid? Yes, the area of the trapezoid. So now I just need to know what is the whole minus 1/100th. It's 99 over 100 of the whole. So this part is 99 over 100 of the whole. Now, how would you find the area of a triangle with 5, 6, and 7? 1 over 100th. I probably said something wrong. But anyway, so I want to have 99 over 100 times a whole. What formulas do I know? Oh, yes, I should use my hero, known as Heron. I actually don't know whether it's hero or Heron. I think oftentimes it's called Heron's formula, but I've also seen it as hero's formula. I need to learn my history. But in any case, I need to use this, that thing. We need to use that thing. So what we have here is that we have a triangle with A, B, and C. So the area is equal to square root of S minus A, S minus B, S minus C, right? Where S happens to be the semi-perimeter. So the semi-perimeter is equal to 5 plus 6 plus 7 divided by 2. That's half the perimeter. That's why it's called semi-perimeter. And to do this, I always like to say 3 consecutive numbers. The sum is 3 times the middle. That's the average. 3 times 6 and then divide by 2. Let's divide the 6 by 2 first. So it's 3 times 3. That's 9. Hopefully that wasn't too fast. You can also see it's 18 over 2. So now let's just get the area. Area equals square root of 9 times 9 minus 5, which is 4, times 9 minus 6, which is 3, times 9 minus 7, which is 2. Now let's go and pull out the square part. Like this part is square. That's 3 squared times 2 squared, so that's 6 squared, and 6 root 6. So that means my answer is going to be 99 over 100 times 6 root 6. Answer, 99 over 100 times 6 root 6. Cancel time. And if I start canceling, divide the 2, that's 50, and that's 3. Whoa, I need to know 99 times 3. Thankfully, that's easy. That's 100 times 3, 300. Just kidding, minus 3. 297 over 50 and square root of 6. And the question asked me to do something with these 3 numbers. Yes, it's just like add the A, the B, and the C. So if I want to add these 3 numbers, the 297 plus 6, that's 303, because this was like 3 less than 300, so adding 6 gets me 3 more than 300. 303 plus a 50, and that gives me 297 plus 6 plus 50 is equal to 353. And that's the answer that I'm going to propose. Let's see if this works. It does! Okay, and so that finishes the problems that we were going to talk about today, because we usually want to leave a little bit of time if there's any random questions that people might have. And as you can see, these questions are pretty interesting. I have to say, I'm very impressed with the kinds of questions that we were playing with. That's, credit goes to the people who made the questions. Amazing. And I'm also very impressed by all of you who managed to not only keep up, but also help me fix mistakes and notice all of the problems along the way. With this, let's move to just some very brief Q&A at the end. Any random questions? Could you please stop spamming? I promise, I'll stop spamming. I see, you're asking something else. Aha. Random questions, random questions. Oh, okay. My parents are convinced that video games turn your brain to mush. Is this true? Well, I'll say anything that you do that doesn't keep making your brain actively come up with new ideas might turn your brain to mush. So it's not exclusive to video games. I think the thing that is good to do is to always be trying to do things that keep you sharp. It's almost like exercise, right? If what you're going to say is, I'm going to keep fit by sitting in my chair, that turns your muscles into mush. So it's the same principle. It's like if you're working on something and you feel that you're actually getting better thinking about something, then it's not going to turn your brains into mush. And with video games, depending on the games you're playing, that might actually be what's going on, like sitting on the couch. Okay. Oh no, somebody said that's me during online school. Oh, I have a random tip for you. If you're doing online school and if you have the capability to turn your camera on, and it's okay and you're lucky enough that you're in a place where you can, if you do that, that actually makes you more engaged, because you will realize that you should be paying attention, and then your brain might not be as much mush anymore. More things. People ask all of these things. Oh yeah, somebody said you never ever turn on your camera, but maybe you should. I'm simply going to say, I know that not everyone has the luxury to do so, so I'm not here saying everyone should. But if the only reason you have it not on is because everyone else has it not on, you don't have to follow them. And honestly, if you have it not on and you're just like off playing video games on some other tab instead of paying attention to your class, your brain might be turning into mush. Okay, more questions. Oh, what is the Heron's formula again? Let me just quickly flip back to that. That was important, right? So the Heron's formula was this way of finding the area of a triangle. In fact, the proof of it is really interesting, but we just didn't have the time to do that in a lesson like this. Heron's formula is up here. Okay. Somebody asked, do I like horses? Yes, I think horses seem neat. I don't know much more to say than that, though. Horses seem neat. Horses seem fast. Horses were very useful at some point. I think I like horses. Okay. More questions. What do most people get on the AIME? A-I-M-E. If most people tried to take the AIME, they would get 0, unfortunately. But if you gave it to just the people who qualified for the AMY, then the average ends up being something more reasonable. I think the average ends up being something like 2 or 3 out of 15. Or maybe 4, maybe, but probably more like 2 or 3. But one of my goals in life is to try to get as many people in the world to be able to do question number 1 on the AMY as possible. Okay. All right. So I think I'm just gonna take one more quick thing here. Yeah, let me hit that one. How do you know that you're good at math? I think I want to emphasize that you don't need to think that you're good or not good at math, because I think that for a lot of people, they're just practicing and memorizing stuff. If you just practice and memorize stuff, then you might think that someone that seems like, they're so good, they seem to be able to do all kinds of things, even stuff that you don't remember. And then you know what? The person's just like not memorizing. Actually, the distinction between good and bad at math, in my opinion, is just a question of, does the person know how to think? It's like what you just saw us doing. The math league questions, they give you a chance to go and practice thinking. That's the entire point. You saw that I would look at the question and I'd be like, oh my gosh, what am I supposed to do here? And that, first of all, makes your brain not turn into mush. But second of all, teaches you how to think. And if you do that, even if you thought you weren't good at math, if you spend a lot of time doing this, you suddenly get really good. And then after a while, everyone's like, my gosh, how are you so good? How are you able to remember all these things? And the secret is, you're not remembering any of them. You're just thinking about them. And a little story, like I do this in my class at Carnegie Mellon, which you're welcome to watch if you want. It's on YouTube, it's for free. It's every Monday, Wednesday, Friday, 2:10 p.m. Eastern time. Next one is tomorrow. And it's just a class for college students. And what we do in that class is we just like do combinatorics, but everyone has to think. And the exams that I give are all exam questions where no one's seen them before. And you just have to think while you're on the exam. The first exam, people usually have a bit of struggling. But by the time you get to the second or third exam, all these people who maybe weren't necessarily used to thinking in this way before suddenly learn how to think. And then they're really good. So anyway, my main thing is I don't think there is really anyone who's bad at math. I just think it's that people haven't practiced thinking yet. All right. Well, that finishes this live stream. I think we're actually going to keep doing collaborations. Not I think. We are going to keep doing collaborations with mathleague.org because their questions are really good. And so the next one will be announced on our channel at some point soon. But it will probably be within 1 month or so. At most 2 months. Hopefully all of you guys had fun. I certainly did. And, well, until next time, see you later. Bye-bye.